Well, it's a pleasure to introduce Al Perger, who is going to tell us about his thesis work on hypersurfaces with central convex cross-sections.
Thank you for Professor Alexander for the invitation. Thank you all for coming. Today's talk is about a classification result. This is actually the non-trivial part of an if and only if statement. So let me first say what the trivial part is. So let's take a circle and put a cylinder over it. And let's assume we intersect this plane with not so much tilted planes. Then I either get, again, circles or ellipses. These are all examples of central ovaloids. Central means there is a there's a point of central symmetry, which such that this thing is invariant under reflection about that point. And similarly, if you take any quadric and intersect with nearly horizontal planes, then you'll again get central ellipses, which are central ovaloids. And this theorem says that if I have an immersed surface having this cross-sectional property, then it is either a cylinder or a quadric. So let me write the theorem. Let's I will say why this is n bigger than or equal to 4 in a second. Be a complete, connected, smooth hypersurface with a central ovaloid property, or COP. I will give a better definition of it, but it is actually just this cross-sectional property, so COP. Then, as I said, then M is either a cylinder over a central ovaloid or a quadric. Okay? So let's go over some of these definitions here. I will give a better definition of an ovaloid, but for now, you can either think of it as a guitar pick. Right? A one-dimensional ovaloid is also called an oval. So this is a guitar pick is an example of an oval, or an ellipse. All right? This oval is not central. There is no center of symmetry. Okay? But on the other hand, ellipse, which is finely isomorphic to a circle, it has a center of symmetry. So that corresponds to the center of the circle. So COP, central ovaloid property. A hypersurface has central ovaloid property if there exists at least one cross-section with a hyperplane, which is an ovaloid. And all such cross-sections are central. So basically, I intersect with a plane, I get an ovaloid, and all such ovaloids are central. So that is the central ovaloid property. And that's all the definitions I want to make for this theorem. So let me first describe the historical background. So where is this thing coming from? Well, it dates back to Brun, 1889. Brun took a convex body, smooth convex body in Rn, bigger than or equal to 3, and he assumed all cross sections to be centrally symmetric. Then he concluded that that convex body is an ellipsoid. Then in 1941, Olav Yanishnikov greatly generalized that result. He took any convex body, no assumption on smoothness, and he assumed the cross sections which divide the volume in fixed proportion, not one, to be centrally symmetric. Then he again concluded that that convex body is an ellipsoid. Then in 1918, now Blaschke, in R3, he took a convex surface, and he assumed that every plane transverse or nearly tangent intersects this surface along a central loop. And then he showed that that convex surface is a quadric. The result that one of the results that I'm more interested today is Solomon's 2009 result. Right? He took a hypersurface of revolution. Okay, let's assume that the axis of rotation is the EN axis. So let me draw one particular hypersurface of revolution. Okay, and then he assumed.
That just means all the cross sections are spheres?
Yes, yes. And then he assumed all nearly horizontal cross sections to be centrally symmetric. Of course, if you take a horizontal one, it is just a sphere, but he also assumed nearly horizontal ones to be central hypersurfaces on M. Okay, they are all transverse cross sections. Okay, so these are just central hypersurfaces on M. Then he showed that M is quadric. So it's a quadric hypersurface of revolution. Okay? This is something very important that I will be using at the end. Okay?
Can you tell us what it means by nearly?
Okay, so nearly, of course, you intersect with a horizontal hyperplane. Then you choose a direction. So this is in n-1. You choose a direction on Sn-2. And along that direction, so if this was the z at height z, so this is n-1 dimensional thing, and you choose a direction, let's say tau on Sn-2, so let it point towards you, right? Having those, I have a small enough epsilon that I can tilt. It depends on, of course, the height and everything else, okay? It depends on the surface. So that's what I mean nearly.
Just there is an epsilon.
Yes, there is an epsilon depending on height z and even the tilt direction. But
wobble that much and get this property, then
yes, yes. Now let's go back to n equals 3, right? And let's assume that our immersed surface does intersect a plane along an oval. Okay? So it's a transverse intersection. Therefore, that surface locally is an embedded tube. Right? You can just flow by the gradient of the height function. So let's assume this is where they intersect, this surface M and the plane. And then I can flow by the gradient of the height function. I get an embedded tube. So since this is an oval, right, then near horizontal cross sections are again ovals, because these continuity of the principal curvatures. And not only that, the nearly horizontal ones are also ovals. Okay? Now, this is what Bruce calls a transverse to convex tube. So let me repeat. A transverse to convex tube is an embedded tube such that each horizontal cross section is an oval. Right? This is called the transverse to convex tube. This is it. So now if I also assume this transverse to convex tube have COP, right, then what it says that all such cross sections are central. Therefore, I have this curve of centers of horizontal cross sections. If it has COP. Okay. So let me call that as T.
I'm losing my grip again. COP, did you write down what it meant?
No, I didn't write it down.
Right, would you write down COP?
Okay. Can I write it here?
Yes.
So it does not take space. So M has.
Sorry, Jeremy. Jeremy came in late and I was actually trying to help him and he can't see where you're writing.
Okay.
Could you put it on that board, please?
Okay.
Thanks.
M has COP if, or central ovaloid property, if there exists a hyperplane H, right, such that M intersect H is an ovaloid. So let's see, M. So this is, we assumed, immersed hypersurface. Okay, that M has central ovaloid property if there exists a hyperplane H, so there exists at least one, such that M intersect H is an ovaloid, and all such ovaloid cross sections are central.
So, there just has to be one?
Yeah, I will only assume there exists at least one.
Because this is immersed, so.
Yes.
All right, but there's at least one that's an embedded overload.
Yes, and it is central.
And if there are any others like that, they are also.
Yes, and yes, whenever I have any other cross section which happen to be ovaloids, they are central.
Okay.
Yes.
What exactly is central? Just
There's a center of symmetry. So there's a point such that if I reflect that that hypersurface or that object through that point, it is invariant. Okay, so this is a transverse convex tube. So what I can also do, so these are, let's suppose these are the horizontal cross sections. They are all central, right? I can actually move them horizontally, right? Such that now the curve of centers is just a line, and that object is called the rectification. So how do I obtain this? I obtain by just translating each horizontal cross section such that their centers lie on the E-N axis. Okay, and this is a rectification of this transverse to convex tube. All right. So having this, Bruce in 2012 showed a theorem whose local version is this. So this is n equals 3, a transverse convex tube with COP is either a cylinder, so a transverse, since it's a transverse convex tube, cylinder means cylinder over a central ovaloid, or a quadric. Okay, and the global version is exactly the n equals 3 case of theorem. So basically, this theorem is a generalization of Solomon's 2012 result to all dimensions bigger than or equal to 3. Okay, and today's talk is about the local version. I will give some idea of proof of how one can do it for the local version when n is bigger than or equal to 3, okay, including 3. And just a quick word of how one can go from local to global. So now I have my immersed surface as I said, locally looks like a transverse to convex tube because it has COP. So locally it is a transverse to convex tube. But now with the local version, that transverse to convex tube is either a cylinder or a quadric. So locally that surface is either a cylinder or a quadric. But then I can expand this again flowing by with the gradient of the height function because the thing is complete. I can extend this tube, and that extension stops only when the tube is exactly the surface because it's connected. Therefore, going from local to global is not anything sophisticated. It's just some technical things one needs to deal with in differential topology. Right? Some flow box argument with this gradient of height function. So, here, okay, so this M, right? This M, I don't assume it to be convex, okay? But it is but locally it's a transverse to convex tube. Therefore, and just because of the definition, it has nearly horizontal convex cross sections, right? Therefore, I am going to be using this. This allows me to use tools of convex geometry. Okay. Therefore, let me give some introduction to convex geometry. Okay. Let me define the things that I will be using in convex geometry. Okay. So convex geometry. A convex body for me is just any non-empty compact convex set. I always denote as K. I don't assume to have interior points. When it has interior point, it's full dimensional. And so if I have a convex body, I can define a support function. Okay. With a support function, I have a support, and I will give I will draw an easy convex body to illustrate these definitions. With a support function, I have a support hyperplane. With outer normal U. And I have the support set, which is the intersection of H and K. The support hyperplane and the body. This is called the support set. Okay? An easy convex body is a solid ellipse. Okay? So now if I now restrict this support function to the circle, right, let this be this unit direction, then what this measures is the distance of the support hyperplane to, or signed distance to the origin. This is the support hyperplane. And the point of intersection is the support set. Okay. So this is a very particular convex body. Well, first thing, it is smooth. Right? We already know solid ellipsoid is a smooth object, and also each support set is a singleton. Right? Therefore, this is an example of a strictly convex body. A strictly convex body which is smooth. But I can also have strictly convex bodies which are not smooth. Right? So if this was the origin, right? This is a strictly convex body. The boundary does not contain any line segment. And now if you were to look at the normal cone, at 0, right? It is not not one-dimensional. Okay, so this is not a one-dimensional cone. So, and therefore, for each normal vector here, I have one support hyperplane that supports k at 0. So this is the characterization of smoothness. A convex body is smooth if and only if at each boundary point the normal cone is one-dimensional, or equivalently the support, or there exists a unique support hyperplane. So this is something not strictly convex but not smooth, and an easy example of a non-strictly convex body is something like this. All right. Now let me give definition of the ovaloid. Okay. Now a formal definition of an ovaloid. And again, one-dimensional ovaloid is also called an oval. Is an ovaloid if there exists, or if it is, let's say, if it is the boundary of a smooth convex body, Km, so K refers to dimension, therefore it has an interior, convex body Kn, such that all principal curvatures are positive everywhere. Right? So, so this is a hypersurface, the non-vanishing Gauss curvature. Therefore, the Gauss map is a diffeomorphism. Right? And here is the inverse. Okay? So for a given outer normal U, this map gives the unique point where the ovaloid makes outer normal U. Okay? So this is from Sn minus 1 to the ovaloid. Oh, okay. All right, let me keep writing this. Okay, now, how do I how do I describe this XKU analytically? Okay, this is the part I skipped, but let me come back to it. Now, now the objective is to get an analytical description of XKU, not just by this description, just by inverse of the Gauss map. And this is where we're going to be using the support function. Okay? The support function has some nice properties. Okay? For example, it uniquely determines the body that it supports. And every sublinear function is a support function. And an important lemma is this. This HK, this support function, is differentiable at U if and only if the support set is a singleton. In which case, that X can be found by taking the gradient of H at U. Okay? Therefore, if I have a strictly convex body, right, each boundary point I can find by just taking the gradient of the support function. Okay? Well, this is a strictly convex body. I mean, the boundary of a strictly convex body. Therefore, this point can be obtained by just taking the gradient of the support function. Okay? So this is how the analytical description of this point. Or if I were to write this gradient in spherical coordinates, This is what I obtain. So this is called support parameterization. Support parameterization of the ovaloid. And I will always denote that as gamma. Gamma of u. Okay? Now, a very important example of support function is this. So if you give me n many positive numbers, ai's, okay, I can construct this function. So with those ai's, right? This is a sublinear function and differentiable everywhere except the origin. Right? Therefore, first of all, it's a support function because it's sublinear, and because of it's differentiable everywhere except the origin, the body that it supports it's a strictly convex body. Okay? And how do I figure out that body? Well, if I know all boundary points, right? The body is just a convex hull. Okay? So what is the boundary points? Well, because the body is strictly convex, the boundary points are just the gradients, right? All gradients of H. And then a simple calculation, after a simple calculation, we'll get this set. Right? Therefore, this is a support function of an origin-centered ellipsoid. Right? And now we have, here's a definition of a support function. It's and from this definition, it's easy to see how the support function behaves when we apply in the rigid motion. Right? Therefore, we have the support function of all ellipsoids. Okay, so let's remember that. And I think this is all I had to say for the introduction. So let me begin with the proof of this theorem, okay, or the main steps. Okay, let's describe the main steps of what one needs to do. Okay, the first thing I had to do is to classify the solutions of this differential equation. Okay? This is the differential equation of interest. I have h squared. And let's put that as a lemma. So let h be a C2 function where n is bigger than or equal to 3. And we'll always refer to the dimension of the outer, dimension of the ambient space. So when I say n3, so this is actually the dimension where Bruce worked. And bigger than, well, if it's bigger than or equal to 4, that's where I work. But this lemma holds even for Bruce's case. Be a non-vanishing function. Then star holds if and only if, of course, plus or minus h is the support function of an origin-centered ellipsoid. Okay? Right? It's nice that we have a h square, and there's a square root. You know, one side is just in easy computation, where you start with that and you take the square and you just find that this thing is constant on the sphere. Okay? That's sort of easy part. The other direction, right? So let's see. I have 20 minutes. No? Yes. Okay. So let's look at the other implication, right? So it is side. So let me denote this L n minus 1, right? So this just means L of h squared is constant, right? But then h squared can be written as sum of a particular solution and a homogeneous solution, h2. Okay? For the particular solution, we choose the easiest one possible, which is going to be c over 2n minus 1 times xi squares. Right? That will make it constant on the sphere, so this part dies, and this just gives me L of h1c. And h2 is the homogeneous one. So what this implies, right? That this h2 is an eigenfunction of the Laplace-Beltrami operator. Right? We all know what they are. So this h2 has a very special form. This is a spherical harmonic of degree 2 in Rn minus 1. So it's some homogeneous polynomial, harmonic homogeneous polynomial, and its restriction is the spherical harmonic. So then h2 is of this form. Right? A is an n minus 1 times n minus 1 trace-free symmetric matrix. And this is h2. Well, because of this wise choice of h1, now I have h squared to be is of this form. Right? B is a symmetric matrix again, but it's also positive definite. Right? So there exists a matrix P that diagonalizes B, and with some computation, you can show that H plus or minus H supports So this is the origin-centered ellipsoid that H or minus H supports. Okay. All right, this will be very important at the end. So let me put that in a box. Okay. Here is it. Yeah, I can erase everything else, I think. Or maybe not. Let's keep this for now. Let's erase this. Okay, so up to now, I haven't made use of COP. So let's use that now. COP will be used to show that the transversely convex tube is a cylinder or a quadric. Okay, so this is the COP implies tube is either a cylinder or a quadric. Okay. So you remember this transverse to convex tube I drew and also its rectification, right? So what I am going to show is that its rectification, right? After I translate all the horizontal cross sections such that the curve of center is just a line segment, I am going to show that that is either a cylinder or a quadric. Okay? Because after I show that, I can actually generalize Solomon's axis lemma to show that the tube, the original tube I have, its curve of centers is just affine. Okay? So if the transverse to convex tube and its curve of centers of horizontal cross sections is affine, so then that means it is affinely isomorphic to its rectification. So but I already showed its rectification is cylinder or a quadric, and of course ovaloids are invariant under affine isomorphisms and quadrics are again closed under affine isomerism. So it is enough to show that the rectification is either a cylinder or a quadric. Therefore, I assume that, a priori, I assume that the curve of centers lies on the n-axis. Right, so this is the curve of centers. Let it have height ranging from -1 to 1. And okay, each horizontal cross section, okay, it's just an ovaloid centered at the origin, right? And I'll denote that as OZ. Z refers to the height, okay? And then, as I said in the beginning, I can then parameterize each nearly horizontal cross section once I fix a tilt direction on Sn minus 2, the height, and the tilt slope. Okay, so here tau is the tilt direction, and z ranges from -1 to 1, and epsilon is the tilt slope. Okay. One more definition. So this is a transverse to convex tube, meaning that each horizontal cross section is an ovaloid. Therefore, I can define this function, which Solomon's and I call a transverse support function. All right, so this is defined as this. For each height z, hz is a support function of the convex hull of the horizontal cross section at height z. So this is called the transverse support function. Okay. Now let's fix tau and z. Okay. This is tilt direction and z. Okay. And let me draw an ovaloid, strictly an ovaloid, tilted ovaloid, right? So an epsilon is small enough. It depends on tau and z, but it's something small enough, including 0. Right? 0 corresponds to horizontal one. So let it be one such ovaloid. So an important observation is, well, first of all, because it's strictly convex, right? For every outer normal direction, u and minus u, there are exactly 2 points, right? Oh, I'm sorry. Why? Oh, should we?
Break the chalk and usually that.
Yeah, well, I don't. Okay. Okay. So, right. This is where it has outer normal u, and this has outer normal minus u. There are exactly 2 points. And what are those 2 points? Well, those 2 points are given by the support parameterization, gamma epsilon minus u and gamma epsilon of u, because of strict convexity. And what do? I take the average. And this is what Solomon calls the centrics. Okay? And this is the midpoint. Well, now it is sort of easy to see that this thing is central, right? If and only if the centric is a constant function. Right? For each u on Sn minus 2, this is central if and only if centric is a constant function on Sn minus 2. Okay? And this is how I'm using centrality. Okay? So therefore, let me write it. So COP means, after I fix tau and z, for epsilon small enough, including at 0, right? That means the centrix is constant, right? So that, but constancy implies that the directional derivatives, of course, are all 0 for all u on Sn minus 2 and for all v direction, right? Well, once I fix u and v, right, this thing is 0 for all small enough epsilons, including at 0. Therefore, I take it, and this thing on left hand side has dependence on epsilon. Okay, so now if I take the derivative with respect to epsilon at 0 and change the order of differentiation, I get this thing. Okay? So, with that, I am going to define another function. All right? So now this function f will depend on tau, that is the tilt slope, u, that u is exactly that u there, and z this way. Right? This is the spherical divergence of this vector field. And it is 0, right? Because the 0 is there. Okay. Right. So now I have to compute what this thing is. Right? That turns out to be quite complicated computation. But what is going to happen really, for example, for n equals 3, what my objective is, so when n is 3, right, this tau lies on the unit circle, right? This thing, and which is also true for n bigger than or equal to 3, but it's much more complicated. For n is 3, what I will get is, so cosine theta, some expression not depending on theta, plus sine theta, not depending something else, not depending on theta, and 0. Right? So this divergence is equal to this, and 0, right? But it is true for all tau, therefore it is true for all theta. Okay, so that just means that not only the sum is 0, but these things in parentheses individually vanish. And what they are, no, they're not the same. I will write what they are now. They are the two PDEs that H satisfies, actually. Okay, for that I have to look I have to look those PDs. Okay, I have about 6 minutes. Okay, so let me write what these things here for all n bigger than or equal to 3. I have those two PDEs. The first one, again, remember h is a function of both z and u. So this is the derivative of h with respect to z. Right, all, so again, these are spherical gradients and spherical Laplacians, and this is the covariant derivative on Sn minus 2 of covariant derivative of this vector field along this direction. So this is the first PDE that H satisfies, so maybe it's one of them, I don't really recall right now. The other one is this, H okay. This is plus. H of Z. Okay, so these are the two PDEs I have.
So we've got Laplacians of H in there and,
Yes.
okay.
Yes, there's Laplacians here, spherical, gradients, and this is the only thing. Well, this is gradient.
You've got a lot of dells.
Yes, this is the vector
One way or
field.
the other, they're gradients, they're Laplacians, and they're covariant derivatives.
This is covariant derivative.
Okay.
These are two are vector fields.
Straightening out what they are.
Yes.
Okay.
And yeah. Okay. So well, the second one looks more promising, I think. That's what we should start with. If you look at it closely, you will see that 2 implies this. Okay, 3 minutes. So, right, because this is this thing is just numerator of this quotient, and H is strictly positive, so everything is good. Now, I think I have to make a little huge jump here. I have 3 minutes. What 2 will serve is that I will be able to separate variables. Okay, using. So if you want to ask after the talk, I can explain a little more. But what I'm going to do is I will use Harnack inequality with some open and closed argument and the connectedness of the sphere to write H as this. Where this only depends on the height. And H1 is the support function of the ovaloid at height 0. So this is how I use the second one. Now I go back to the first one, right? If now I have this H, I have this H is R and R times H1. Now if you look at each of, so I have 3 summands here, right? 1, 2, and 3. So each one has exactly R and R prime factor, right? For example, if you look at this, R prime comes from here, R comes from these. Well, R prime comes from this derivative, and R comes from here. R comes from here, R prime comes from here, and again, R prime comes from here, and R comes from here. So, and everything else is some expression only involving H1. Right? So now so I have this thing just turns out to be some R and R prime of Z, and everything else here is some expression only involving H1. Now if this transverse to convex tube is already a cylinder, right, then I'm done, because that's something I want to show, right? If it's a cylinder, then I'm done. If it is not a cylinder, right, that R has to change. Because if R is constant, well, I have the same horizontal cross-section, right? So, but if R changes, right, this R prime at some height is non-zero. Well, I look at that height, so this is R Z naught, R prime Z naught. This is just H1 involving U, and their product is 0. So I get rid of this thing, right? So now I have something, some PDE satisfied by H1, right? But
Most of this thing you got rid of.
R and R prime.
Okay.
You said
Yes.
R prime isn't 0.
Yes.
And this is an equation equal to 0.
Yes. I cancel that.
And that leaves his.
And that PD just turns out to be equivalent to this one. There, yes. Therefore, H1 is the support function of an origin-centered ellipsoid, right? Because here I have classified all solutions of it. Then I go back to here, to this, and then I have all horizontal cross sections they're just the same positive homothetic copy of the same ellipsoid. Therefore, it is affinely isomorphic to a hypersurface of revolution, which has COP, right? Then I go back to Solomon's 2009 result and conclude that it is actually a quadric hypersurface of revolution. And right on time. Thank you.
Questions? This approach does not really look like what people doing convexity were expecting, I suppose.
No.
How does it compare with what Solomon had to do in the three-dimensional case?
Well, I mean, the overall argument sort of mimics his argument. Okay? So what is overall? Well, we first show that locally it is true, right? Locally it is either a cylinder. That's also what he does. And then from local to global, that differential topology argument has no dependence on.
This argument with Harnack.
No, that is new. That is fine. No, that he, in his case, of course, because of his dimension that he worked, much more simpler, and he used some other thing to get the splitting. Okay, but for higher dimensions, that approach was meaningless. So this is using Harnack's inequality to get the splitting. That's something new. Okay. But he also, again, the general argument is the same. He also tried to get the splitting, and again, refer to his 2009 paper at the end. So actually, I don't show that this is a quadric. Okay, I just refer to his 2009 result. I just show it is a hypersurface of revolution.
Thank you again.
Thank you.